So it gave us an error because the data that we have input and that we have just used for the new prediction. So this one, it doesn't have the state dummies basically, and that means the model is expecting this sort of an output, but it's getting something else. So we can easily fix that if you just open this file in Excel. It's going to take a little bit, and just enter some values, some zeros and ones. Oh, sorry, let's do 0. Let's zoom in a little bit. So 0 and 1 and 0, and let's do this here. And of course, only one of these has to be 0, and the names don't matter. So this was California, Florida, New York, but we can use any labels. It's not going to have an impact on. It's not basically, we're not going to read the labels. So we save that, Control S, and let's load it again. Click on here, import this again, wherever you have it. It was on my desktop. So now if I rerun this, see, we have these variables here. And if I run this now, it's going to give me predictions for these two inputs. So this was it for the linear regression, though there is one point, one thing that we mentioned in the lecture, and right now it's not going to have really an impact on the model because it's a very small data set, but there is something off with the data set, the X that we're using to train the linear regression. So you can pause and think about it for a moment. It has to do with how we dummy encoded these three variables. Let me bring up the slides. So we were saying one of the assumptions in linear regression, so here it's not really checking the assumptions, but is multicollinearity. So that means one of these variables would be completely correlated with two other ones. So what does it mean? So when I want to encode a categorical variable with 3 levels, and I've created 3 dummies. So one of them is redundant. Basically, let's go a little further up when we did this. So here. So these are the 3. So for example, this row is New York, California, and Florida. If both these are 0, I know that this will be 1. So it's going to be New York. One of these has to be 1. So if these 2 are 0, and that means this observation is in the state of New York, this startup. So this is always the case. Whenever you're encoding a dummy, you need one. If you have if it has 3 levels, you need just 2 dummies. If it has 4, you just need 3. You always need 1 dummy less than the levels of the categorical variable. So let's do this. Let's drop New York. Still, we know that this observation is New York because it's a 0, 0. So basically the baseline of the model. So if both of these are 0, it's going to, we're talking about a startup in New York. So how do we do that? So remember this line, we were using it to drop the state. So I'm going to just copy this, create a new, I'm going to do it below this cell. Create a new code cell, Control V, paste it. And here I'm going to change the column to New York. And I'm going to run this. I'm going to take a look again. So New York is gone. And let's do so you just only need to change this. We're going to resplit the data. So let's split it again so that the train and X-test and X-train have the correct shape. They're basically without New York. Let's take a look. Yep, it doesn't have New York. And let's run the regression. Basically load, create a new instance, fit it on the new data set, create the predictions. For this one, I'm going to copy it so that I still have the previous results from the previous one. So I'm going to copy this cell, and I will just use this and paste the cell. Oh, let's do Control V. Let's put one up. Okay. So now if I rerun this, and you see we get the same values here. So it's not impacting the predicted performance in this case. But if we would look at the coefficients, they might be different. So let's do that. Let's take a quick look. It might just be that in this case, in here, it doesn't matter because the number of observations is, oops, Python is sensitive to indentations. Okay, let's run this again. Oh, yeah, now both of them are going to show me the new results. But it doesn't matter. So this was just to show you, in terms of predictive performance, they're going to do the same here. But it would be good practice to not have a redundant dummy encoded variable. Okay, so this is it for the linear regression model. I'm going to comment this out again. And so we're going to train the rest of the models with this new data set that does not have New York. And let's see, we won't be able to use this right now. It's going to give us an error because, again, now I have only 2 dummies. So we can fix this again just to be able to use this new input. I'm just going to open it this time in Notepad because it's, oops, no, let's close this. Okay, so this last column I'm gonna delete. You can do it in Excel. If you do it in Excel, just delete the last column. I'm gonna save it again and upload this again, the 2 inputs. And now let's load it. Now it's gonna work. So let's talk about the next model. So the next one, pardon me. So the next model we talked about in the lecture was the decision tree regression. So we're gonna load it from sklearn decision tree regressor. Then we're gonna instantiate a new class. Again, the random state is set to a value so that we get the same results. So, and then we're gonna basically fit this decision tree regression on the same training set. So let's do that. So this is the model is trained now. And you see there's a bunch of metrics that we can, so these are basically the hyperparameters for the decision tree model. So we're not gonna get into details of it now, it's just get started. And now let's evaluate this model. So I'm going to just look at, so the first line is, it's the same you had in the previous cell for linear regression. The difference only is here we're gonna name this y_pred underline dt, so the predicted y's using the decision tree. The reason I'm using different names is later on we want to compare these models. I'm gonna run this, okay? If we compare it with what we had, let me clear this. So which one do you think is better so far? We go with the one that has a smaller RMSE or MAE. So the linear regression did a better job. So next we're gonna, so the random forest regression, again, we are calling it from the sklearn library. So if you remember, I mentioned the random forest regression is a ensemble learning model. So here we are creating a new instance of this model, and I'm specifying here the number of trees. Remember, we had to specify the number of trees, and this is the stopping threshold. So we say minimum sample leaves is going to be 1. Let me just comment this out and run this cell first so that we can see the, okay, this is what I wanted to show you. So you see the, if I move my mouse, it goes, okay, now here we are. So it shows you what sort of parameters it takes. Number of estimators, this is the number of decision trees. The criterion to use for the splitting of each tree. So we had it also for the decision tree. Remember, we were talking about, and the decision tree algorithm is basically trying to create leaves that are more, that have less variation or are more homogeneous. And how is it doing this? So here, the default metric is mean square error. That's what it's using. And here, mean square error. And it says this is equal to variance reduction as feature selection criteria. And this is, we could specify the depth. This is how deep the tree goes. And it has, so there are a bunch of different variables that we can tune. So, and okay, this one, the minimum samples leave. So this is the minimum number of samples. Remember, I was saying one of the ways to stop the tree from learning is to specify what's the minimum number of observations you want in a leaf in order to keep it. The default is 1. That means it's going to just keep going. We can change it and see what happens. So I'm going to keep it to, let's keep it 1 and run it, and then we can rerun this with 2 and see how it does. So I'm going to uncomment this line. So it's going to initiate this random forest model and then train it on this data set. So fit means it's going to fit it on the training set because I'm providing the training set as input. So let's do that. Okay, it's trained. And do that again. That's only... Oh, okay, it doesn't... It's okay with the shape. This is basically how our Y is shaped, but it says I would prefer if you would reshape it to so that it looks more like what it is expecting. And here now with the trained model, we're gonna do, again, let me comment out this line. I just want the RMSE and the mean MAE. Okay, these are the values. So let's see what happens if we change this. So I'm gonna do, let's say 3, and then retrain this whole model. And then it was, so it was, RMSE was 8440. Okay, it went up. So the precision went down. The predictive accuracy went down. So let's go with the 1. And keep in mind, we're dealing with a very small data set here. And let's rerun it. Let's rerun this so it keeps these values here. And the last one, let's recall the support vector regression. And to do that, I need to, so remember when we were talking about support vector regression and support vector machine, we said we need to scale the data. So this model is sensitive to the scale of your variables. So we're going to scale, basically scale all our variables so that they are in the same range so this model would work correctly. It's still going to produce results if you don't scale your data, but the problem is the results aren't reliable. So let's run this. So this line is importing this is the pre-processing library from sklearn. So I'm pulling the standard scaler and the min-max scaler. So these were the two that we mentioned. Let me take you to this corresponding slide. It was over. Yeah, the feature scaling. Let me maximize this. So the min-max normalization and the standardization. These two scalars, we're calling these two scalars from the pre-processing library here. And what this does is, so I'm calling them both, but I'm using the standard scaler. So I'm initiating the scalar, and then I'm saying I'm creating two separate ones. The reason is I want to use one of them to transform that to inverse transform my predictions so that I can compare them. So we'll see in a few minutes. So both of these are scalars basically. So what they're gonna do is they're gonna scale a data set. This one is a standard scalar, so is the SC, basically the scalar on the line X. So what we're doing in this line is we're taking the X train, and we're transforming it using this scalar. So this is what it does. So let's say the scalar that I initiated, I'm fitting it and transforming it on this X train. So it fits, it's basically looks at the shape of this data set, and based on that, it's also going to transform it. And this is the result, basically X train is C. So just to see how it looks, let me create a separate code cell and show you the output. So this was X train before transformation. So this is X train after transformation. The only thing is it's not giving you this nice data frame view because it changes it to an array, and this is the format we need to feed it to the model. But if you just go over these numbers, you will see they have a mean of 0 and a standard deviation of 1. So if I run this, it's gonna X train SC and Y train SC. These now contain the scale data set. So let's just take a look at this guy and run it. So this is scaled. If I look at Y train, this is the it says uppercase Y. So this is the unscaled data. You see the range is to be going up to 120,000. That one, it just goes still. I can check. Let's see. Yep, -2. Or we could just do this. Anyway, it's fine, it's scaled. We know it is scaled. And so let me delete this cell. And now that we have the scale data set, we're going to call the support vector. From the support vector machine library, we're going to import SVR. This stands for support vector regression. We're going to start a new instance of it with the RBF kernel that we talked about a little bit in the last slide here, using this kernel. And now then we're fitting it on the transformed data set, this one. So we're going to run this. It has a note for us. It's again about the shape of the Y column, which is, it's still going to do the job. It just would prefer us to reshape the data. So it has a format it prefers. So this is trained now. Let me just clear this output. And here what we are doing is, so we want to use this model to do the prediction. But since we use the transform data set to train the model, we would need to also transform the testing set. So that's why I was creating separate transformers, because this one is looking at the shape of the Y data set, which is just one column, basically one variable, but the X is the collection of how many variables did we have? We had 1, 2, 3, 4, 5. So this is, let's get back to here. Yeah. So that's why I had separate scalars. So now here it's going to use that same scalar that was used to transform or rescale the training set to transform the testing set, this part in here. And just to show you, I'm going to copy this, create a separate code, and just show you what this is going to do. So it's going to scale the data. And with the transform data set, this is what I'm going to feed now to the trained support vector regression. I'm again saying support vector regression dot use the predict method. So basically predict for a new input, produce a prediction using this model here, and the input is the transformed testing set, and it's going to name it ypred. And now ypred, so ypred isn't going to have the actual values. So it's not going to have the values of profit in the original scale because we have done a prediction with the transformed rescale dataset. So what we need to do is basically apply the inverse transform. So take it from the transformed scale, the standardized scale, back to its original scale. And that's again the reason I created a separate scaler for the y, so that I could use it to inverse transform the predictions. So before we can just run this, and let's just take this line. Let's take ypred and take a look at it in this cell. So you see the range of these values. So remember the profit was ranging, it had numbers around a couple 10,000, 100,000. But these are these are the transformed values at a different scale. And when we transform them, like basically we apply the inverse transform. We're taking the y's from the standardized scale, we're putting them back in the original scale, and we name it ypred underline SVC, and these are now in the original scale. See, the numbers look more reasonable to what we had in the data set. So, and then it just, the rest is the same, and let me comment this line again. It's just calculating the mean squared error and then taking the square root. Here it's the mean absolute error. The values are, let me rerun this. These are the values. Okay, so let's see how we can compare. So remember I saved all of these prediction. I used different names. So these are all the predicted y values for the testing set. So now I'm going to, here we're just going to import the pyplot from the matplotlib library. And this is just an array of names. These are the 4 different models that we did. We did a linear regression, a decision tree regression, a random forest regression, and a support vector regression. And this is an array that's going to contain the predictions that we produced after running each of these models. So remember ypred line from Opter, ypred predicted y's using the decision tree, the predicted values, y outcomes using the random forest, and the ones that we just did with the support vector regression. So, and this result is just an empty array. Here I'm just saying go over each of these and fill these and add the RMSE to this array. And then at the end, I'm going to just use a bar plot to visualize and compare these. So let's run this. So, okay, here it's the linear regression, the decision tree, random forest, and support vector. And these are the RMSE values. So which one do you think does a better job? So remember, we're going to pick the one that has the lowest RMSE is the best one for prediction purposes. And that takes you to question 2. Which model would have a better predictive performance? So seems to be the linear regression. You could run this to look at the values if these seem too close to you, but we can already see this is slightly lower, so this is 7,073. And remember, we were saying that when we talked about these metrics, let me go back to the RMSE, we said express the average model prediction error in the same unit as the outcome variable. That means the units of this error term, so 7,000, is in the same unit as our outcome, which was dollars. So for example, if the profit is predicted to be $100,000, it has an error of about 7,000. Standard error of about 7,000. So question 2 then, put your answer here. Which model did a better prediction? So here I was using the RMSE. I was basically populating this array with the RMSE values. So question 3 asked you, now use the mean absolute error, and so then see which model based on MAE would have the best performance. So let's do that. So we're going to just go back to this cell over here, And the only thing you need to change is, I already put in the code. You can delete, just comment out this line and uncomment the MAE. So this is the same line that we had in the previous cells. See, it's this one here. And I'm just saying, yeah, calculate the mean absolute error. From the y-test is the same, but so here I'm just using a loop to basically loop over all these values. It's going to take y per linear, then y per dt, then y per RF, and so on. And then in the end, I'm rounding them up to 2 digits so that we don't have too many decimal points. Then I add it to this array, and then the rest is going to be the same. And I'm just, we're going to also change this to MAE, then rerun. So these are the MAE values. Something looks a little off. Oh, this is because I didn't change this over here. MAE. Okay. So now, well, and if I click on results, okay, again, the linear regression does the best job in for this small data set. So 5,256. So again, you can add and provide your answer here, and that's going to be question 3. And once you're done, make sure to save your notebook with your answers. And so you should have run all these cells and done, like you can play around with it. But in the end, once you also have your answer and have run the cells, click on File, save it. And before we wrap it up, and the mean absolute error, that metric is also in the same unit as the outcome. So that means this is basically $5,256 because our outcome variable was profit and it was in dollar terms. So let's say if the model predicts for a new input, so something we did up here, let me go up and up and up. Okay, here. So if it predicted the value, the profit for this firm with these numbers for the spending is 86,550. So the linear regression had a mean absolute of 5,256. So that means the predicted average profit for this firm is about 86,500 with an error of about 5,250. So that's it, and make sure to save your notebook again. And once you're done, just download the notebook, the Python notebook, after you've saved it. Here. And you can also download, if you want, the I'm going to keep it, the Python code. This one you could open directly in, say, a textpad editor or something. It would be readable. The Python notebook, you cannot open it in the text editor. And then just go to the Dropbox on eLearn, go to the Dropbox for activity 1. If you had sent any submissions for activity 1 before, I have deleted them because you didn't need to submit anything for the getting started with Colab. And oops, sorry, I need to change my view. So you're just going to go to the Dropbox and activity 1, and then just add the file from your computer. You can click on upload, or you can just drag and drop. I'm going to say wherever you've downloaded these two, you can just drag and drop them. If you want to put in your Python file as well, that's fine, do that. And then just click add and then click submit. And that's going to be it for activity 1.